So for this learning module, we'll go about the process of computing the moment of a force about an axis. So as is described in this motivation slide, for the majority of physical applications, computing the moment of a force about an axis versus a point is really what's of the most interest. If you think about if you're trying to loosen a fastener in this situation using a socket wrench, what you're trying to do with that tool is apply a force to induce a rotation that would actually loosen the fastener. So the component of the moment that you're interested in is how much rotation you induce about an axis, which is aligned with your fastener. So just know that in most physical situations, you're more interested in the computing a moment about an axis than a moment about a point, as we've done until now. So the good news is that the process is very similar to computing the moment of a force about a point, as you may expect. And just like the point-based examples, you can also take a scalar-based approach. And the scalar-based approach just kind of gives you the best intuition of what we know on our day-to-day life. Unfortunately, I'm sure the majority of us have used a lug wrench before to loosen lug nuts. And in that case, we know that the longer the wrench, the less force we have to apply. So in this case, what the text is trying to show you is if you have an example where you're trying to compute the force about an axis of interest, which in this case is the y-axis, because it's aligned with that nut that you're trying to loosen by applying a force to your tool. If you happen to know the perpendicular distance from your axis to the line of action of the force, which we would here, right? That's just going to be the length of our wrench. We can compute the moment of the force about that axis by just taking that perpendicular distance and multiplying by the perpendicular component of the force. So it's a really long way to say that back when you first learned this in physics class, probably maybe sometime in high school or even earlier than that, that your idea of torque is exactly analogous to what the book is calling the moment of a force about an axis here. Like all of the geometrical approaches, it's a bit tough to do in 3 dimensions, either because in the 2D drawings that they give us, you just can't see the information, or you're just not provided with enough information to be able to compute that perpendicular distance easily. So we do like the vector-based approaches, even though they're more cumbersome, because we can do them the same way every time. And speaking of those vector-based approaches, the way that we compute the moment of a force about an axis is to first compute the moment of a force at any point along that axis. So this is, again, one of the key ideas in computing the moment type chapters is that there's a lot of degrees of freedom for you to actually choose. So on the axis, we can pick any particular point we want. Once we compute the moment of the force about that point, we'll just take a dot product with a unit vector along that axis. In addition, we can kind of write that operation that we just talked about in a simpler approach, which is known as a scalar triple product, or a triple scalar product, as your book calls it. And what that does is it just gives you a formulation to do exactly what we said, compute a moment. Remember that a position vector across a force is always going to be a moment. And when you take a dot product of that, you're obviously going to get a scalar with a unit vector. Remember back to the prior chapter, when you take a dot product with a unit vector, you're getting the component of whatever vector it is along that axis. So it's really just dressing something up and making it look complicated, but it's the same idea that we've looked at up until now. So let's look at an example problem. We're applying a force at the geometry, which is shown, and I have it printed out, so we'll be able to write directly on it. But if you notice, the geometry that we're given is both some linear dimensions that will allow us to compute the point of application of the force, along with these angular descriptions. And if you look at what's drawn, and if you look very closely, probably easier to see on the slide than the printout that I have, what we have are angular displacements from the 3 principal axes, the X, Y, and Z axis, to the line of action of our force. So if you remember back to chapter 2, we called those the coordinate angles, and we said that when you take the cosine of those, that's the direction cosine, and that's one way that you can always decompose a force into rectangular components, or if you know its coordinate angles or its direction cosines. So let's actually look at how we would go about doing that. I'm going to go to my .cam here. So we'll do it with both approaches. First approach said, if you want to compute the moment of a force about an axis, just pick any point along that axis and compute the moment of the force about that point. So if I'm interested in the x-axis, the first thing I have to do, step 1, is to pick a point along the x-axis. Now, oftentimes in book problems, you're going to be restricted by the information that you're given. So if you look at the 2 linear dimensions that you're given, they're just kind of the only point that they will allow you to compute a position vector from on the x-axis is the origin. So we're forced here to the origin And of course, the origin point O has coordinates of 0, 0, 0. But fortunately for us, that's going to be a convenient thing to be forced to do, because when we compute the moment about that point, recall that we need to define a position vector from the point of interest to anywhere along the line of action of that force. So I could define it to the point of application. That might be an easy thing to do based upon the information that I have. But if I had additional information, I could choose that position vector to be anywhere along that line of action. Please don't forget that. So I'm just going to compute the position vector from the origin to point A. So I'll say ROA. And if you notice, in order to do that, I will need the coordinates of A. So as point A is drawn, notice it's in the YZ plane, meaning that its x coordinate is 0. In order to go over to point A, I would need to go over in positive y by 0.3 meters. So x coordinate is 0, y coordinate is 0.3. And once I get there along the y-axis, I would go up by 0.25 meters. So I can write a position vector from the origin to A by just taking the x coordinate of A, subtracting the x coordinate of the origin, weighting that by I hat. What you find is that whenever the tail of your position vector is the origin, you can write the position vector very easily by just writing the coordinates of your tip point. And that makes sense intuitively. If you think about it, what it says is to go from the origin to point A, you take displacements in x, y, and z that are just equivalent to the coordinates. So no displacement in x, go over 0.3 in y, go up 0.25 in z. So that physically makes sense. Step 3, all that we need to do is compute the moment about that point. And we will do that by taking the cross product of the position vector and the force vector. Now, how would we define what that force vector is? Well, we can remember that we can always decompose any force vector if we know its coordinate angles by weighting each by its directional cosines. So any force can be written as the force magnitude times a unit vector directed along its line of action. And in this case, what we're going to do is take the force and multiply by a direction cosine unit vector that's equivalent to the cosine of each of these coordinate angles. So it's just a matter of going up and seeing what angles we were given. If you notice kind of from the axis, which is parallel to the x-axis, we're told that there's 120 degree displacement to the line of action of the force. So it'd be cos 120 I hat, and then plus cos, what is the coordinate angle for the y-axis? Well, the y-axis in this case, the geometrical information that we're given is that this axis, which is parallel to y, it's a 60 degree displacement from that axis. So that would be 60 degree j hat. And then finally, for the z-axis, we're told that it's a 45 degree displacement. So let's actually compute what that is. And I will go to MATLAB in order to do this. And I ran through it beforehand. So let me just say that the force is equal to 200 times cos d of 120, cos d of 60, cos d of 45. And that turned out to be minus 100, 100, and 141 point. I'll carry a little more precision, even though I'm going to be using the values that are stored within MATLAB. So what is that? Just to make sure that we're good, well, that is the force, and it would be in units of whatever unit the magnitude was, which is in newtons. Let's make sure that the signs of the components make sense. It says that this force is directed in the negative x direction. The negative x direction, that looks right. Let me zoom out a little bit, that way you can see. Negative x direction, positive y direction, definitely agree with that, and positive z direction, definitely agree with that. So this force looks like we use the angles correctly, which we did. So finally, to compute the moment, I'm just going to take the cross product, and I can use that 3 by 3 matrix that I talked about, which I compute the determinant of. So that would be in the first row, the position vector, 0, 0.3, 0.25. In these, that should have been in the second row. In the third row, the force vector, minus 100, 100, and 141.4214. And remember, do a cofactor expansion, cover up the first column and the first row, take the determinant of that 2 by 2 matrix, that's your I component, minus cover up the second column and the first row, take the determinant of the 2 by 2 matrix. So we won't show that again just because that will get a little bit long if we do. So I'm just going to define my position vector in MATLAB. Feel free to use your calculator to do this. Got it. And what I want to take is the cross product of R and F. What I find there is that this is equal to 17.42, and since I'm just going to take a dot product with the unit vector, I'll round to 3 sig figs since that's usually what we report. So let me go back to my .cam and you can see what I've computed. So this is the moment of that force in Newton meters about the origin. So step 4, all that I need to do is take a dot product with a unit vector along the axis of interest. So if we want to compute the moment of this force about the x-axis, our unit vector is just going to be I hat, and m dot I hat is just going to give us the x component of this vector, which is just going to be 17.4 Newton meters. So what that is saying is that this force, when it's applied, it's going to tend to induce a rotation in the counterclockwise direction about the x-axis, corresponding to a magnitude of 17.4 Newton meters. So let me show you how to do the triple scalar product. This is the approach 2, in case you wanted to do that. And you're doing the same thing. It's just, it's rolling all of the work into one operation. So if you go back to, and I'll just show you on your slides how you would do this. There we go. So there's the formula for the triple scalar product. You put the components of the unit vector along your axis in the first row. So think about it. What would it be for our axis, the x-axis? Well, the unit vector along the x-axis is just I hat. So the entries in the first row will just be 1, 0, 0. The entries in the second row will be the same as our position vector when we computed our moment. And in the third row, we'll have our force components, minus 100, 100, and 141.242. Now look at what happens here when you go back to looking at this written on the .cam. If you were to do a cofactor expansion and determine the determinant of this matrix, remember the way you do it is you cover the first column, first row, take the diagonal of the matrices, and then repeat that repeatedly, right? But what will happen here is that so let's just write it out real quick. So this would be 1 times determinant of 0.3, 0.25, 100, 141.42, right? Minus 0 times whatever that determinant is, right? Let me just write it in for you real quick. 0, 0.25, minus 100, 141.42. And the reason I'm writing so sloppily is whatever this determinant is, when you multiply by 0, you're just going to get 0. And that same thing happens for the third term as well. You take the determinant of this matrix, but you scale it by 0. So that'll be 0 as well. So what do we get here for this determinant? We get 0.3 times 141.42 minus 100 times 0.25. And if you compute that, take the products and take the differences, you would also get 17.4 Newton meters. So that will check out. So it's the same calculation that you're doing. This is just a mathematical approach through the triple scalar product that makes the mathematics quicker.